EMT, or electrical metallic tubing, offers several advantages over ENT, electrical non-metallic tubing. Firstly, EMT is noted for its ruggedness. It is a rigid conduit providing significant mechanical protection for the wires contained within it. It exhibits greater resistance to crushing and impact compared to ENT. Secondly, grounding is another critical advantage. EMT provides a continuous electrical path, which is essential for effective grounding. ENT, conversely, does not offer grounding capabilities. Thirdly, pulling ease is improved with EMT. The smoother interior surface of EMT facilitates easier wire pulling. Fourthly, cost is also a factor. Generally, EMT is less expensive than ENT. Now, let's consider if ENT can be used in place of EMT. Yes, ENT can serve as a substitute for EMT in specific applications, but there are limitations. The first consideration is strength. ENT is not as robust as ENT. Therefore, it should not be installed in areas where it could be exposed to physical damage. The second consideration is grounding. ENT does not provide a grounding path. It should not be used in applications where grounding is a requirement. The third consideration is pull strength. ENT's smaller wire pulling capacity may require the use of a pull string or smaller, more flexible conductors, depending on wire size and pull lengths. So, where can ENT be used? ENT is suitable for dry interior locations concealed within walls, ceilings, or floors, behind finished surfaces like drywall or plaster, and in areas not subject to physical damage. Where is ENT prohibited? ENT should not be used in wet or damp locations when exposed to weather or corrosive environments where grounding is required, or in areas subject to high levels of physical damage. ENT is commonly employed in residential and commercial construction scenarios where there is no necessity for grounding or mechanical protection. It is lightweight and flexible, simplifying installation, particularly in confined spaces. However, it's crucial to acknowledge its limitations and apply it judiciously. In conclusion, ENT is generally the preferred choice for the majority of applications, offering superior ruggedness, grounding capabilities, and ease of wire pulling. ENT is suitable for specific dry, concealed locations where grounding or mechanical protection is not essential. Regarding NEC, the National Electrical Code, specific articles govern the installation and use of both EMT and ENT. Article 358 addresses EMT, while Article 362 covers ENT. These articles outline the approved uses, installation requirements, and restrictions for each type of conduit. For EMT, approved uses include both exposed and concealed work in dry, damp, and wet locations under certain conditions. It can be used in all atmospheric conditions and occupancies unless specifically restricted by the code. Some restrictions include locations where subject to severe physical damage unless protected and were exposed to destructive corrosive conditions. Suitable raceway and fitting shall be used. EMT must also be supported according to the requirements outlined in 358.30, which specifies maximum distances between supports. For ENT, its use is primarily limited to concealed dry locations. It can be used in walls, floors, and ceilings where not subject to physical damage. It is often used in residential construction for branch circuits. However, it cannot be used in exposed locations, hazardous locations, or where subject to physical damage. It is also prohibited in theatres and assembly halls unless specifically permitted by the code. Support requirements for ENT are detailed in 362.30, and it must be securely fastened in place. When considering the suitability of EMT versus ENT, it is important to evaluate the specific environmental conditions and potential hazards of the installation location. EMT offers superior mechanical protection and is suitable for use in areas where the conduit may be subject to physical damage. ENT, on the other hand, is more flexible and easier to install in tight spaces, but it lacks the mechanical strength of EMT. In terms of grounding, EMT provides an equipment grounding path when installed with listed fittings. This is essential for safety and to prevent electrical shock hazards. ENT does not provide an equipment grounding path, so a separate grounding conductor must be installed within the conduit, Choice between EMT and ENT also depends on the type of wiring being used. EMT is suitable for use with all types of conductors, including THHN, THWN, and XHHW. ENT is typically used with smaller gauge conductors, such as 14 American wire gauge and 12 American wire gauge, but it can also be used with larger conductors if the conduit fill requirements are met. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC specifies maximum conduit fill percentages to ensure that conductors can be easily pulled and that heat buildup is minimized. When selecting conduit size, it is important to consult the NEC tables for conduit fill to determine the appropriate size for the number and size of conductors being used. For example, Table 1 in Chapter 9 of the NEC provides dimensions and percent area of conduits and tubing. Tables 4 and 5 specify the maximum number of conductors in EMT and ENT respectively. The selection of fittings is also an important consideration. EMT fittings are typically made of steel or aluminum and are designed to provide a secure connection between the conduit and electrical boxes or other equipment. ENT fittings are typically made of plastic and are designed to be easily snapped together. It is important to use listed fittings that are specifically designed for use with the type of conduit being installed. Listed fittings have been tested and certified by a recognized testing laboratory to meet safety standards. Installation practices for ENT and ENT also differ. EMT is typically cut with a hacksaw conduit cutter and then reamed to remove any burrs or sharp edges. The conduit is then bent to the desired shape using a conduit bender. ENT is typically cut with a utility knife or PVC cutter and then bent by hand. It is important to follow the manufacturer's instructions for installing both types of conduit. Proper support is essential for both EMT and ENT. ENT must be supported within 3 feet of every box, fitting, or termination point, and at intervals not exceeding 10 feet. ENT must be supported within 3 feet of every box, fitting, or termination point, and at intervals not exceeding 3 feet. Proper support prevents the conduit from sagging or becoming damaged. When transitioning from EMT to ENT, a listed fitting must be used to connect the two types of conduit. This fitting must provide a secure connection and maintain the integrity of the grounding path. The NEC also specifies requirements for bonding EMT and ENT. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault current. This helps to prevent electrical shock hazards. In summary, the choice between EMT and ENT depends on several factors, including the environmental conditions, potential for physical damage, grounding requirements, type of wiring, and installation practices. EMT offers superior mechanical protection and grounding capabilities, while ENT is more flexible and easier to install in tight spaces. It is important to consult the NEC and follow manufacturer's instructions when installing either type of conduit. Remember to always prioritize safety when working with electricity and to consult with a qualified electrician if you have any questions or concerns. The ampacity of conductors in conduit is also a crucial consideration. Ampacity refers to the current carrying capacity of a conductor. The NEC specifies ampacity ratings for different types of conductors based on their size, insulation, and temperature rating. When conductors are installed in conduit, their ampacity may need to be derated to account for the effects of heat buildup. The NEC provides tables for derating conductor ampacity based on the number of conductors in a conduit and the ambient temperature. It is important to consult these tables to ensure that the conductors are not overloaded. Overloaded conductors can overheat and cause a fire. The voltage drop in a circuit is another important factor to consider when designing an electrical system. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop in a branch circuit should not exceed 3%, and voltage drop in a feeder should not exceed 5%. To minimize voltage drop, conductors should be sized appropriately and circuits should be kept as short as possible. When running conduit through fire-rated walls or floors, it is important to maintain the integrity of the fire rating. This can be achieved by using fire-stopping materials to seal any openings around the conduit. Fire-stopping materials are designed to prevent the spread of fire and smoke through penetrations in fire-rated assemblies. The NEC specifies requirements for fire stopping in Article 300.21. When installing conduit in concrete, it is important to protect the conduit from corrosion. Concrete is alkaline and can corrode metal conduits over time. To prevent corrosion, the conduit should be coated with a corrosion-resistant material or encased in a non-corrosive material. The NEC also specifies requirements for the burial depth of underground conduits. Underground conduits must be buried deep enough to protect them from physical damage and to prevent them from freezing. The burial depth requirements vary depending on the type of conduit and the location. When installing conduit in hazardous locations, such as areas where flammable gases or vapors are present, it is important to use explosion-proof conduit and fittings. Explosion-proof conduit and fittings are designed to contain any explosion that may occur within the conduit system and to prevent the ignition of flammable materials in the surrounding atmosphere. The NEC specifies requirements for hazardous locations in Articles 500 through 516. When working with electricity, it is important to always follow safe work practices. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing circuits before working on them. It is also important to use properly insulated tools and to avoid working in wet or damp conditions. The NEC provides detailed requirements for safe work practices in Article 110. The selection of the appropriate conduit type is a critical decision in electrical installations, impacting safety, costs, and long-term performance. While ENT offers robust protection and inherent grounding capabilities, ENT provides flexibility and ease of installation in specific scenarios. A thorough understanding of the NEC guidelines, along with a careful assessment of the application requirements, is essential for making an informed choice.